Alright, let us continue with the titration of weak acid with a strong titrant. Now we have covered the calculation before equivalence point. So today we will look at the calculation at equivalence point. Okay, so how do we calculate pH at equivalence point of a titration between weak acid and strong base? So the approach is not the same as strong acid, strong base, where the equivalence point is pH 7. Okay, for weak acid and weak base, the calculation involving the conjugate. Okay, so in this example, we start off with a weak acid. So therefore, at equivalence point, all of the weak acid has now been converted to conjugate base after react with the strong titrant, which is sodium hydroxide. So when it's converted to conjugate base, means no longer benzoic acid. Okay, so we have to find the new concentration of the conjugate base. So in this case, it's benzoate. So to find the concentration, we have to use Kb relationship. Okay, Kb relationship. So to find Kb, in which Ka was given, so we use the Kw expression. Okay, so Kw equivalent to Kb times Ka. So to find Kb, Kw divided with Ka. So this would be the Kb value. Now, at equivalence point, okay, how to calculate the concentration of the benzoate? Okay, we use this relationship here. Okay, so at equivalence point, number of mole of the benzoic acid present in the Erlenmeyer flask, okay, is the same as the number of mole of the titrant, which is sodium hydroxide. So we have to find the number of mole first. Okay, so to find number of mole, and M divided with to find number of mole, M times V. Okay, so N equivalent to MV. Okay, so we have to find this first. Okay, so M of benzoic acid is 0.1 molar, volume is 100. So does the titrant. Titrant 0.1, volume also 100. So number of mole would be 0.1. Okay, so N is 0.1. Okay, now using this number of mole, we can calculate the molarity of the benzoate. Okay, so to find molarity, okay, same formula, M molarity would be N divided with V. Now V have changed because the 100 ml of sample already mixed with 100 ml of the titrant. So V now becomes 200. Okay, so substitute the 0.1 mole here. Okay, the concentration of the benzoate now is 0.05 molar. Okay, now what next? Okay, using the Kb expression, using that concentration of benzoate, okay, substitute it in the expression here to find X. X here would refer to OH. Okay, OH means the benzoate concentration. Okay, so X is 2.81 times 10 power of negative 6 molar. So we negative log this, we get POH, which is 5.55. So to find pH, we minus from 14, which is 8.45. So this is agreeable because the sample is weak acid. Titrant is a strong base, so therefore the equivalence point will lies on the basic region. Okay, if your sample is a weak base, your titrant is a strong acid, means equivalence pH will lies in the acidic region. Okay. So this has been plotted, okay, when it reached 100 ml of titration or equivalence volume. So next is over titration. So for the calculation involving over titration will be similar to strong acid, strong base titration. So the same. It's the same. Okay. So you can use this formula here. Okay. Finding OH concentration. Okay. And then you minus from 14 to get the pH. Okay. So now the new volume is 210. Okay, so this is the concentration over titrate, which is 10 ml after titration, 10 ml excess of titrate. And continue with 20, 30, 40, 50. Okay, and the plot should look like this. So you see the pattern will be similar, despite the titration is between weak acid and strong titrate. So if you start with the weak base, you get curve like this. Okay, so that if you start with a weak base sample, okay, strong acid titrate. Okay, for titration involving polyprotic acid, okay, the name itself poly imply that it has more than one ionizable proton. Okay, so means you will expect more than one inflection point. So this is called inflection point, okay, in the titration curve. So this is example of phosphoric acid. Okay, so for this phosphoric acid, 50 ml of 0.1 molar was titrated against a strong base sodium hydroxide 0.1 molar. Okay, so based on this information, we can find the equivalence volume of sodium hydroxide needed, okay, to titrate the sample here. Okay, so means M1V1, M2V2, we will expect 50 ml of sodium hydroxide. Okay, and to react with the remaining H plus, we would expect another 50 ml of titrant. Okay, to react with the remaining H plus. So here you see two inflection point. For polybasic base, also the same case, mean it has more than one OH, okay, that can be react with the titrant. Okay, for example, here is sodium carbonate, okay, 25 ml of 0.1 molar, okay, titrated against 0.1 molar strong acid, hydrochloric acid. So you see there's a two inflection point here. Okay, so next we look at evaluation and selecting the endpoint of a titration procedure. Now, equivalence point, or theoretically, okay, occur when stoichiometrically equal amount of analyte and titrant react. So M1V1, M2V2. However, endpoint is determined experimentally. So we do the experiment, and normally it exceeds the theoretical value. Okay, so any difference between the two value means the endpoint and equivalence point is a source of determinate error. So for most acid-base titration, the inflection point, okay, of experiment titration will nearly coincide with the equivalence point, the theoretical value. Now, what is the important point in acid-base titration is the inflection point, but somehow there's a limitation in order to locate the inflection point. Okay, there are cases inflection point missing or difficult to detect because of very small acid dissociation constant Ka. So if you see this figure here or graph here, okay, pKa1 you can still is the best inflection point we can see here, but as the value of Ka increases, means the as the value of pKa increases, so means the value of Ka decreases, the inflection point becomes narrower, and until at one point the limit pKa 11, it's gone. Okay, we cannot see. Okay, another situation where inflection point is missing or very difficult to detect is when the analyte or the sample is multiprotic. So it can be polyprotic acid or polyprotic base. Okay, for example here, malic acid is an example of polyprotic acid. Okay, so you can see two nice inflection curve here, where pKa1 is 1.9, pKa2 is 6.33, and then Ka1 is 20,000 larger than Ka2. Okay, here is another example of polyprotic acid, which is malonic acid. So we can see that the first inflection point is not really visible here. Okay, and the difference between these two is Ka1 is 690 times larger than Ka2. Okay, and this is the value of pKa1 and pKa2. Okay, let us look at a third type of polyprotic acid, which is succinic acid. So succinic acid actually have more than ionizable proton, but based on this curve here, we can only see one inflection point, means pKa1 and pKa2 is too close. Okay, or we can say the Ka value for 1 is only 27 times larger than Ka2. So generally, okay, we need the pKa different to be at least 2.7, or by a factor of at least 500, this one. So we can visibly see the different inflection point. Otherwise, like the case of succinic acid here, somehow the first pKa, the first and second inflection point merge. Okay, too close. Next, let us move to indicators. Okay, so what is indicators? So indicators are highly colored weak acid or weak base. Okay, so you see here, okay, this is one color. When it reach the end point, it changes to a different color. Okay, so this is example of weak acid indicator, H. Okay, H indicator. Okay, abbreviated as H indic. So you have H plus and indic. Okay, some indicator, like I have shown in the earlier lecture, have more than one color transition. For example, methyl red, it changes from yellow to orange and then red. Okay, and the one that you are very familiar with is phenolphthalein, where it changes from colorless to purple or very pale pink color. So what is the purpose or the role of indicators, okay, in acid-base titration? So they act as additional weak acid or weak base. But it must be weaker than the species being determined. Mean that this weak acid has to be weaker than the sample. So let's say your sample is strong acid, strong base, then it won't be any issue because these indicators are weak acid and or weak base. But if your sample is weak acid, the indicator has to be weaker than the weak acid used. Otherwise, it will interfere with the titration. Okay, and the indicator also has to be at very low concentration. That's why when you do acid base titration, you only add 2 to 3 drops only indicator in the titration, in the analyte. Okay, don't put too much, otherwise it will interfere with the acid base titration. Okay, another property of indicators that it must give a sharp and distinct color change. Distinct color change means it's permanent. Okay, if you swirl the sample or the analyte in the LMA flask, you didn't get a permanent color change, then you still have to add in more titrant. So this is what happens when you put too much indicator. Okay, when you plot, you get this wavy inflection point. Yeah, you should get a straight, nice inflection point. But when you put too much indicator, you get this kind of curve here. Now, how to select the right indicator when you do acid-base titration? Okay, like I mentioned just now, we have to use smallest possible amount. Okay, just enough for us to see the color change. Okay, and the indicator used should not significantly start to undergo color change until we have passed the equivalence point. So what does it mean here? That the color range change for indicator has to be above the equivalence point. Let's say for strong base titration, the equivalence pH is expected to be at pH 7. So the indicator used should change in the pH region more than 7. Okay, so that's why you use phenolphthalein for acid-base titration, because it change, the color change is in the basic region. Okay, past the equivalence point. Now the average analyst will observe a color change when about 1/10 of the indicator converted. Okay, so the pH conversion of 1/10 of the indicator is this. Let's say you start from basic condition, means basic sample. Okay, so it should be, the pH is calculated using this relationship, pH equivalent to pKa minus 1. Okay, if you start off with acidic sample, okay, pH is equivalent to pKa plus 1. Okay, so that's why the transition range for indicator is pKa plus minus 1, depending whether it's acid or basic sample. So ideally, our indicator's pKa is 1 unit above the pKa of the sample itself. Okay, so if the sample is base, then the pKb or pKa should be 1 unit lower. Okay, we seldom find a perfect indicator, so we use the one that is about minimum 1 unit away. Okay, for example, phenolphthalein that you normally use or you are familiar with, it change in this pH range 8.3 to 10. So in strong acid, strong base titration, the end point should be around pH 7. So we use phenolphthalein, because it's 1 unit above, about 1 unit above than the equivalence pH. Okay. So some cases we mix the indicator, or we add neutral screening dye to indicator to give narrower range. Notice that the earlier slide, the range is quite big. So when you mix indicator, we narrow the pH. Okay, so that it will be more specific for the acid-base titration. Okay. Okay, let us look at one example here. Okay. So the indicator used here is phenolphthalein and bromothymol. Okay. Why bromothymol is an inappropriate selection of indicator for this titration of acetic acid and sodium hydroxide. Okay, acetic acid is a weak acid, sodium hydroxide is a strong base. Okay, based on equivalence pH, it should be around this point here. So if you use bromothymol blue, it will change color at this point here. Okay, it's supposed to change color in this region here. That's why phenolphthalein is a more appropriate indicator use, because the pH range for phenolphthalein is about this point here. Okay, so phenolphthalein is a good selection. Okay, 1 unit higher if the sample is acid. Okay. So this video is example of different indicators and the color change at different condition, basic or acid. So you can watch this video on your own free time. So you see here, this is example of titration curve using methyl red indicator and also phenolphthalein. So phenolphthalein color change interval is this region here, while the equivalence pH is this point here. Okay, so by rule we should use phenolphthalein, not methyl red, because it will change before the equivalence point. Okay, so usage of methyl red is not suitable in this case. So phenolphthalein is the best choice. So titration error, or to be more specific, is determinate error. Okay, this is where the titrant is added in excess, or it's more than the theoretical volume. Okay, so how to minimize determinate error is by adding blank sample. Okay, so that blank sample will have the same solution volume and the same amount of indicator, and then the volume used to neutralize or to react with the blank will be subtracted from the total amount of titrant needed by the sample. Another type of error is indeterminate error. So indeterminate error is very difficult to avoid, because different person will have different way of observing color change. Okay, so notice that when you do titration experimentally, your group member will obtain different volume than what you obtain. Okay, because different person will have different evaluation. Okay, so that is unavoidable. Okay, indeterminate error. However, if we have a blank sample, it will minimize the problem. Okay, or we can prepare a reference solution. Okay, a reference solution is a type of blank sample. Okay, and we adjust it to the exact pH for the desired endpoint. Okay, besides using visual indicator, which somehow can also interact with the sample or the titrant, due to excess addition of indicator or the wrong selection of indicator, we can use auto titrator instead. Means we don't need to put indicator, okay, only the analyte of interest, and then you titrate. Okay, so how is auto titrator function? The pH will be measured by the electrode immersed in the analyte solution during the titration process, and then we can compute the difference in pH divide with the difference in volume, and also the difference of the difference in the pH over the difference in volume. Okay, and the first derivative, okay, is maximum. Second derivative you get 0. Okay, so that will be the endpoint. Okay, okay, the first derivative from the earlier slide just now is the maximum point. So this is the maximum point for the first derivative, whereas for second derivative the endpoint is the one that at 0 here. Okay, so if you look at the normal titration curve, we would estimate the endpoint to be around here. So means the second derivative is more accurate. So if you use normal acid-base titration and there's problem with your indicator like this curve here, it's not the inflection point, it's not smooth. Okay, probably due to excess usage of indicator. So auto titrator is a good option to determine the endpoint. So how to determine the first derivative is the difference of pH divide with the difference of volume. So let's say here the first point and second point, the value of pH is this and this. Okay, so the difference in terms of volume is this. Okay, based on here, so you divide. Okay, divide the difference of this. Let's say the difference of this is in terms of the pH is 0.002, for example. Okay, so 0.02 divide with difference in volume. Let's say this one is about 3 minus 2 mil, so 1 mil, so 0.01. The second derivative is calculated based on the difference of that we have calculated here over the difference of volume. Okay, let's see, let me just quickly scribble here. Okay, let's say this one. Okay, first derivative, let's say we take the whole number, so easy for you to see. Let's say the first reading here, okay, let's say pH is 1. Okay, let's say pH 1. The second reading pH 2, so 2 minus 1. Okay, let's say the difference in terms of volume, let's say 3 mil, the second one. Okay, the first one is 2 mil, so 3 minus 2, so this one becomes 1. Okay, let's say we see the difference between 0.2 and 0.3, so we do, let's say 3 minus 2, for example. Let's say we take 4 minus 2, and this one 2, 5 minus this one just now 2, right? So sorry, 3, so minus 3, so this is 2 over 2, or also equal to 1. Okay, never mind, equal to 1. So the second derivative is calculated based on the difference of this. Okay, based on the difference of this. So this one divide with this one. Okay, 1 divide with 1. That will be the second derivative. And we do it for the other points here. Okay, so that's what it means by first derivative and second derivative. Okay, next we look at the application of acid-base titration. Okay, first of all, let's look at inorganic analysis. Okay, so inorganic acid or base which are too weak to be analyzed by normal aqueous acid-base titration can be analyzed by adjusting the solvent or by indirect analysis. Okay, for example, titrating boric acid, okay, this is weak acid with sodium hydroxide is limited because of the very small acid dissociation constant of boric acid. See the Ka value too small, so this can be increased, okay, to 1.5 times 10 power negative 4 when we add mannitol. Okay, so after adding mannitol, then we get a better or sharper endpoint. Okay, other example of acid-base stoichiometry for inorganic analysis, standard method for determination of alkalinity, acidity, and free carbon dioxide in water and wastewater analysis. For organic analysis, one good example is determining protein by using Jadal method. Okay, so the correct pronunciation is actually keldai. Okay, bunyi macam keldai. Okay, so Jadal. We normally pronounce as Jadal. Okay, so Jadal method. So in this method, the sample is first digested with mercury oxide as a catalyst, potassium sulfate, and also concentrated sulfuric acid. This is to convert the nitrogen content in the sample into ammonium ion. Okay, next the mixture is boiled until it turns clear. Once it turns clear, we wait for another 30 minutes. Okay, the boiling. Okay, then after that, stop. Okay, stop the source of heat, let it cool down. Okay, after cooling, water and 4% weight of volume potassium sulfide added. This is to remove the mercury oxide catalyst. And then sodium hydroxide is added to convert the ammonium ion form to ammonia. And this ammonia is distilled into a flask containing a known amount of standardized hydrochloric acid. Okay, the sample that has been distilled into the hydrochloric acid will react based on the amount of ammonia that has been distilled. So the remaining or the excess hydrochloric, okay, that did not react, okay, will be titrated with the standard solution of sodium hydroxide. And this step here will require methyl red acid indicator. Okay, so if you look at the step of Jeda method, is actually a back titration example. Okay, so how to calculate the protein content in the sample? Okay, so different protein will have different amount of nitrogen. Okay, and to calculate the protein of the sample will depend on the source of the sample. So if your sample is from cereal source, then we have to multiply 5.7 gram for every gram of nitrogen in the sample. And if the source of the protein is from meat, then this is the factor. And if from dairy product, this value 6.38 is the factor. Now example of calculation. So we have wheat flour. So we know this group belongs to which category just now. So this amount, okay, analyze using Jeda method. The ammonia formed by addition of concentrated base after digestion with sulfuric acid distilled into 25 ml of 0.04977 molar of hydrochloric acid. Then the excess hydrochloric acid that did not react, okay, from this 25 ml, back titrated with 3.97 ml of sodium hydroxide at this concentration here. So the question is asking for you to calculate the percent of protein in the flour. So how do we go about this question? So first of all, we need to find the excess just now. So the excess means we have to minus. Okay, so initially we have 25 ml of hydrochloric acid at this concentration, and when it is titrated against sodium hydroxide, this much of sodium hydroxide is used. So we need to find the difference between these two, okay, to find the excess unreacted hydrochloric acid. So the difference of the unreacted mole is these two here. So 1.2433 minus 0.1593 millimole. So we get 1.085 millimole. Okay, because we want to calculate the nitrogen which actually represent protein. So we times with atomic mass number of nitrogen, because this is in millimole, so this one is also has to be converted in millimole. But my suggestion is, when you calculate this, better you use mole instead of millimole. Means you convert this into liter and this one into liter, so that your final answer will be in mole. So when it is in mole, you don't have to convert this into millimole. You just times by 14, which is the atomic number of nitrogen, and this is the original amount of sample. Okay, times by 100 because you want to find the percentage of nitrogen. So the percentage of nitrogen here would be 2.1341%. But the question is asking for protein, and remember this is flour, so flour from wheat, it's a wheat type, so the factor is 5.7. So 2.1341 times 5.7, so you get the percentage of protein here. So I want you to try this exercise. Okay, so this will be counted as your attendance. Okay, finding the percentage of protein in cheese sample. Okay, answer is given there. Okay, so the step in order to get this answer should be similar to the previous example. Okay, let us see in terms of scale of operation for acid-base titration. So volume of titrant needed to reach equivalence point is proportional to the analyte present. So M1V1, M2, V2. So the smallest concentration analyte that can be analyzed is 1 times 10 power negative 3 molar. That is the smallest concentration we can use. Okay, and we can even use smaller volume. So the smallest volume that has been used is 20 microliter. In terms of accuracy, we can say the acid-base titration is quite accurate because the relative error is only 0.1 to 0.2%. Only the limitation is the difference between endpoint and equivalence. Okay, of course that is due to determinant error that we normally cannot avoid. In terms of precision, we can also say the acid-base titration is quite precise. Okay, under optimum condition, precision of 0.1 to 0.2% can be accomplished. In terms of sensitivity, acid-base titration, it can be increased by decreasing the concentration of the titrant. And if it involves polyprotic sample, okay, we titrate it to a later equivalent point, means the later inflection point. In terms of selectivity, acid-base titration, they are not selective. Mean as long as you have acid and base is good enough. Okay, provided the titrant has to be strong. Okay. Unlike gravimetric analysis that you have covered, for nickel dimethyl dioxide, for example, DMG. It is very specific. Okay, so DMG only react with nickel. Like acid-base titrant, they are not selective as long as you have acid and base, provided the titrant is strong type. Okay, let us look at time, cost, and equipment. So acid-base titration by right is one of the quickest technique. Okay, and in term of availability, no problem, because simplest glassware needed. You only need burette, you only need aluminum flask, you only need volumetric flask for the solution preparation. Okay, unlike when you use instrument, you have to wait for the availability of instrument. Okay, in term of titration, when we use pH meter to identify its equivalence point of endpoint, we only need pH meter which are quite cheap compared to other high-end instrument. Okay,